hopefully we can start now. And we are still missing one of our presenters, though he's apparently in this session and seems to be active. So I hope he'll join us quite soon. Sushmit, if you hear us, please send the request to share your video and audio. Otherwise, we will have a discussion on 4 very lovely papers. Hopefully we'll have a discussion on 5 lovely papers. And in fact, we have 2 of the papers that had received, here is Sushmit, just a second. Hello.
Hi, can you hear me?
Yes, we can hear your sound.
Sorry, let me fix my camera in a moment. I didn't realize I had to click through this button. Thanks.
No problem. So we have 5 papers on applicability of machine learning approaches and data-driven approaches in design. And out of these 5 papers, 2 actually have received the Reviewer's Favorite Award. This means that these 2 papers were rated among the top 10 papers in the whole conference. So congratulations to those authors. I will once again announce that when the presentations are played. Sushmit and the rest of you could please mute your mics while we play the presentations. So we will first play the pre-recorded presentations, and then afterwards we will have a discussion on all of the papers. And so please, all of you who have questions, feel free to enter your questions in the chat. Indicate who you're asking by selecting an at sign and then write the name or the number of the presentation. And then we will either invite you to join us on the podium to further elaborate your question, or we will just answer the questions and discuss them a bit further if you're satisfied with just remaining silent in the chat. So without further ado, I would like us to start with the pre-recorded presentations. So first presenter is Molla. Molla is a graduate research assistant in the Department of Mechanical Engineering at University of Kansas. And his research interest lies in data-driven design, decision-making in engineering design, and computer-aided design.
Hi everyone, I am Molla Hafizur Rahman, a PhD candidate from the University of Arkansas. The topic of my presentation is a reinforcement learning approach to predicting human design actions using a data-driven reward formulation. At the beginning, I will discuss about the artificial agent. We know artificial agents are capable of solving well-defined design problem, but the research shows that human can perform well in tasks like abstract reasoning or finding intuitive explanation for the design decision. Therefore, it is a significant potential to partner human design thinking with a state-of-the-art computation algorithm in a human-AI collaboration framework. Existing design agent developed using deep learning technique or any other method could not provide an optimal feedback. The potential of reinforcement learning is not fully explored in design field, although reinforcement learning has been used in many areas. Therefore, the objective of this study is to develop a reinforcement learning based approach to constructing design agent for mimicking human design behaviors. Next, I will briefly discuss on the topic, on the technical overview of the reinforcement learning, particularly the Q-learning method. The Q-learning is a temporal difference-based reinforcement learning, where a combination of Monte Carlo method and dynamic programming is used. The equation shows the formula for updating Q table from the previous Q value and the reward functions. Here, A denotes the state action space and S represents the state space for the agent. The equation takes values from the Q table and provides the probability for taking each possible actions at a given state. Alpha is the learning rate and gamma is the discount factor. We also used a probabilistic model for predicting next actions. The actions take values from the Q table and provides probability for each possible actions. Here, theta determines the agent decision-making strategies. To compute a data-driven reward mechanism, we conduct design experiment using energy 3D. Here, the design problem is building a energy plus home. The design objective is to maximize the annual net energy while minimize the design cost. So we have set other requirement and constraint for this problem. So the total participants are 52 and data was collected in JSON format, and average line of data is 1500. And here is a one line of design data. Here we collect the design action data for this problem. Now I will briefly discuss on the state, action, and reward formulation for our study. State is the current situation in which agent interacts with environment. In our study, since our goal is to mimic human design behavior, we define the state in RL as the state of designer thought process during design. The proposed state representation is inspired by function behavior structure design process model. The left figure here shows the original FPS model, and the right figure actually shows our proposed FPS inspired state representation. The action in our RL problem are design actions performed by designers. We observe that designers can perform similar categories of actions in each state. We group similar design actions into a few categories. For example, addition of components such as add wall, add solar panel, etc. is categorized by add action. The reward is the feedback from the design. The RL agents aims to maximize the total reward that is calculated by summing all the immediate rewards. In this study, we formulate the novel data-driven reward by leveraging first-order Markov chain model. We average all the transition probability matrices from all the designers to obtain the final reward table. Here, the table shows the reward table. The figure shows the overall research approach. From the sequential data, we define action and state as discussed previous slides. We get a reward from the transition probability matrix, and we update the Q table from the reward table. Finally, we use probabilistic model to obtain the predicted action. Now I will briefly discuss on the model setup and evaluation method. We choose Markov chain as our baseline model. For hyperparameter settings of Q-learning, we trial and error to set the final parameter. Particularly, we set learning rate as 0.3, discount factor as 0.6. We take total 10,000 iterations to train the Q-learning agent. We use theta from 0 to 0.3 with 0.1 increment. The equation here shows to calculate the prediction accuracy. Here, NCP is the currently predicted actions, and L is the length of the total designer sequence, and we take the average of 50 prediction accuracies. We pick 10 highest and lowest performing designers and compare their prediction accuracies. The left figure shows the high performance design group, where total 9 designers have better accuracy than the baseline model, a baseline Markov chain model, which is 41%. In this group, the highest performer, G05, achieved the highest accuracy. The right figure shows the low performance designer group, where 5 designers out of 10 were lower than the baseline accuracy. We also compare the transition probability matrix of the highest performer and the lowest performer in high performance group. The transition probability of G05 indicates that this designer uses edit to edit heavily, which is 0.82. Also, G05 indicates only a specific design pattern. For example, he did not use analysis to analysis repeatedly, while F12 uses analysis to analysis several times. It indicates that the high performance designers follow a specific design pattern, while low performance designers use different design patterns. In conclusion, our contributions are in twofold. First, we formulate a data-driven reward mechanism for Q-learning by leveraging first-order Markov chain model. And second, the design agent provide important design behavior. For example, high-performance designers follow certain strategies. In future work, we will leverage transfer learning to identify the efficiency of design agents in other design tasks. Thank you, everyone, for being with me.
Thank you, Molla, for the presentation. I remind everyone that you can ask the questions for Molla in the chat. while we move on to the next presentation presented by Sebastian, who is a research assistant at the Friedrich Alexander University of Erlangen-Nuremberg. I really apologize for the way they pronounce that. Before that, he obtained master's and bachelor's degree in mechanical engineering from the same university and has completed 2 internships, one in Bosch and one in Continental Engineering Services.
Hello, my name is Sebastian Bickel. I'm a research assistant from the FAU Erlangen-Nuremberg at the Institute of Engineering Design. On behalf of my co-authors Benjamin Schleich and Sandro Wartzack, I would like to present our paper with the title A New Projection-Based Method for the Classification of Mechanical Components Using Convolutional Neural Networks. I want to start with a short introduction. The general idea of part classification is to train a machine learning model and then retrieve a class label for a given input. The classification is based on the geometrical features of the component itself. Because a label database is necessary for the training, it is defined as supervised learning. The determined component label can subsequently be used for further automation in the product development process, therefore saving time and money. Convolutional neural networks, or CNN for short, often provide the basis for component recognition. The special types of neural networks are derived from the human eye by applying multiple convolutional and pooling layers to the input. In general, component classification procedures can be distinguished by the input format for the CNN. In the tree diagram shown here, the 3 types can be recognized in the first level, which are voxels, point clouds, or images. In the second level, specific methods are listed as examples. Current benchmarks show that especially methods with images as input achieve particularly high accuracies. Therefore, images are also used as input for this new approach, but they are generated through a prior projection of the point cloud. Now I would like to give an overview of this new procedure. It all starts with an input geometry, in this case, a meshed surface. This part is then submitted to the geometry preprocessing step, in which the component is oriented through the principal component analysis, followed by a random sampling of points onto the surface. For this study, a point cloud number of 25,000 points was used. This leads to the geometry transformation. In this phase, the projection method utilizes the information of the individual points and projects them onto a detector sphere. This globe is divided into several areas, which are called pixels. Finally, the projected points per pixel are counted and, similar to a map, the generated sphere is unfolded, resulting in an input matrix for the machine learning process. The resolution of this input matrix can be chosen, and in this case, 256 by 256 was used because most of the CNNs have a similar input resolution. 3 different projection types are analyzed in the study, first from the center of the part, second in the normal direction of the points, and third the distance method, which uses the same projection way as the center projection, but instead of counting the numbers of points per pixel, the mean distance between the center and point is used. Afterwards, these matrices are the input for the CNN. For the training, transfer learning is applied, which uses pre-trained networks on the ImageNet dataset as a basis. 5 different networks are examined in this paper: the Inception ResNet, ResNet 50, DenseNet 201, InceptionNet, and the AlexNet. After the finished training, the model is capable of determining the relevant class for a given input, but of course, the input must be preprocessed as stated. Therefore, a new part must also be transformed in the matrix beforehand. Before presenting the classification results, a short description of the dataset is necessary. It is called the Mechanical Components Benchmark and was developed and published by Kim et al. In 2020. For this comparison, the MCBA dataset was applied, which consists of nearly 60,000 parts sorted in 68 classes. The parts are aggregated from trace parts, 3D warehouse, or grabCAD. The components in the dataset are mainly standard parts or components from the mechanical engineering domain. This picture shows randomly selected parts from the dataset varying from screws and washers to clamping jaws. For a good comparability, the dataset is pre-splitted into test and training datasets. After the general overview of the method and the benchmark dataset, I would like to show the results of the classification. Like mentioned in the general overview, different projection methods and CNN architectures were tested. The best combination was the normal projection and the DenseNet 201 model pre-trained on the ImageNet dataset. The achieved test accuracy was 96.65, and the last step was the comparison with the current state-of-the-art methods. In the bar chart, the test accuracy is shown for the different methods, where the new approach is colored in yellow. The achieved accuracy is very high and only surpassed by the RotationNet with about 0.7%. All other methods applied to the MCBA dataset have lower classification accuracy, which shows the competitiveness of this new procedure for classifying components from the mechanical engineering environment. Now, to finish the presentation, I would like to give an outlook for possible applications of the part classification. In this simple theoretical example of a gearbox, the new colors show the parts with the same class label. This information can lead to new approaches to enhance the product development process or support existing ones. For example, an assembly similarity search based on part contact graphs could be improved through the part labels and therefore enhance the assembly retrieval results. Furthermore, an automated FEM preprocessing would be possible by combining the part labels to the derived knowledge database from simulation guidelines. Another idea is to use the component class for a function-oriented surface reconstruction, which should result in a better quality of 3D scans. Now, thank you for your attention, and I'm looking forward to the following discussion session. Thanks.
Thank you, Sebastian. Next is Binyang. Binyang's son is currently a postdoctoral associate in the Department of Mechanical Engineering at MIT, and the focus of her research is the data-driven design and human-AI hybrid teams. She works with data in multiple modalities such as text, images, sketches, and graphs through machine learning algorithms.
Hi everyone, my name is Binyang Song. I'm a postdoc from the Department of Mechanical Engineering at MIT. In this presentation, I'm going to introduce our research titled Assessing Machine Learnability of Image and Graph Representations for Drone Performance Prediction. In recent years, with the success of convolutional neural networks, or CNNs, in computer vision, image has become the most used representation in many fields, including engineering design. Here comes the question. Is the most used design representation the most effective? Indeed, we don't know. Graph is an emerging representation good at capturing relations between system elements. It has been used and proven effective in studies related to e-commerce and molecules, etc. However, we haven't explored it as a design representation, and we know little about its effectiveness compared to images in this regard. Accordingly, this paper aims to answer how do design representations affect what AI can see from engineering designs for design evaluation. For investigating the effectiveness of images and graphs as design representations, the study uses the two representations to present drone designs. Then, I employ convolutional neural networks, or CNNs, and graph convolutional networks, or GCNs, to learn the image and graph representations respectively. Compared to CNNs learning the pixel patterns of images, GCNs capture graph features using the node features and the relations between them. Both models are trained to predict drone performance, including flying range, velocity, and cost. The training data of this study is a set of drone designs created by human designers from previous drone design experiments. The experiments were conducted using a drone design platform developed by our research team. The drone performance simulated in the drone design platform was used as the ground truth to train the deep learning models. The drone design space is defined by a 13 by 13 grid. A component such as motor-rotor pairs, battery, and airfoil from the predefined component pool can be added to any node within the grid. Each component has multiple size options. A simplified example drone is shown here, and the figure on the right shows its visualization in the design platform. In the image representation, the component type, component size, and payload at each node position are represented by 3 pixel matrices, resonating with the RGB 3 color channels of images. In the graph representation, the component type, component size, and payload information is conveyed in the node embedding, which is a non-dimensional vector. The positional relations between components are embedded in the link weights. Then I use a CNN and a GCN to learn the image and graph representations respectively. With the same number of convolutional layers, the GCN has much fewer trainable parameters than the CNN. Results show AI can see more from the graph representation than from the image representation. We can see for all performance metrics, the GCN achieves lower mean squared prediction errors and higher predictive validities, as measured by the R-squared values. That is, the graph representation is more effective than the image representation. 2 reasons explain the effectiveness of the graph representation. First, compared to the image representation, the graph representation can capture the interactions between components far away from each other, since there is a direct link between them. Second, the GCN has much simpler architecture and much fewer trainable parameters than the CNN. Therefore, the GCN can avoid overfitting better. To sum up, this study contributes to the design society in 3 ways. First, it contributes a generalizable graph representation for engineering design. The representation applies to general configuration designs, such as robots and chassis. Second, the effectiveness comparison between the graph and the image representations inform and encourage us to think more about design representation selection for deep learning tasks. It also contributes a CNN-based and a GCN-based regression models for accurate and fast drone performance prediction. The models can be integrated seamlessly into deep generative design models to facilitate automatic design synthesis and optimization. An open question remaining in this domain for future research is how to encode the physical relations between system elements into graph representations more effectively. That's all of the presentation. Thank you for your attention. Questions are welcome.
We can reflect on that open question in the discussion later. The next presentation is by Michael, who is presenting estimation of composite laminate ply angles using an inverse Bayesian approach based on surrogate models. Michael is 30 years old. He studied mechanical engineering and earned both bachelor's and master's degree at Friedrich Alexander University of Erlangen-Nuremberg. Since 2017, he's a research associate at engineering design at the same university under supervision of Professor Sandro Wartzack.
Hello, everyone. My name is Franz. I'm a research assistant at the FAU Erlangen-Nuremberg. My presentation with the title Estimation of Composite Laminate Ply Angles using an Inverse Bayesian approach based on surrogate models is the outcome of a collaboration with our colleagues at the Technical University in Munich. Digital twins are defined as a virtual dynamic representation of a physical system, which is connected to it over the entire life cycle for bidirectional data exchange. So we have a physical part and a virtual part who can exchange data and, for example, use it to control a product or predict the lifetime or the next maintenance. To get precise predictions, virtual models with a high degree of detail are needed. Therefore, measurements, for example, of manufacturing variations are useful. Non-destructive methods are necessary to remain the function of the product. For composite structures, the laminate parameters of the single stacked plies define the structural behavior, where variations of these can be very critical. To measure the inner structure, non-destructive methods like micro-CT, ultrasonic, or thermography can be used. However, inverse material characterization is a rather new approach to infer parameters indirectly from different measurements. This is, for example, used to calculate Young's modulus from measured eigenmodes. Our research questions raised in our contribution are: how can inverse characterization be used to quantify laminate properties in composite structures? Where are the limits of inverse characterization of composite structures? And how can potentials of inverse characterization be used in the context of Industry 4.0 and digital twins? The method is built to inversely infer laminate ply parameters from strain measurements of plates. These are forwarded to the solution algorithm together with a parametric model, in our case classic laminate plate theory, with the ply angles as parameters. Optionally, further surrogate models like Gaussian distribution can be used to reduce computational times. The solution algorithm calculates the most likely solution by fitting the model parameters to result in the measurements using probability distributions. The Bayesian inference representing the inverse problem consists of three main parts: the posterior, which is the resulting distribution, the likelihood, which represents the current likelihood of the distribution, and the prior, which is prior information like nominal parameter values. The solution of the inverse problem leads to calculated ply angles, which can then be compared to our measured true angles. Benefit of the Bayesian inference is that it can overcome typical challenges of such an inverse problem, like ill-posedness, measurement errors, and further parameters subject to variations, leading to additional noise. Next, I want to shortly present you a general example estimating the laminate ply angles. A benefit of the Bayesian inference is the prior information. This means, for example, the nominal parameter values can be included in the calculation. To show the influence on the results, we set up a 4-layered model with 2 loads and solved it using the Metropolis Hastings sampling, which is a solution algorithm for Bayesian inference. As a result, we obtain a sampling and the corresponding likelihoods. In the picture, you can see the results of our estimations with and without prior information. On the diagonal, the resulting distributions of the parameters with and without prior information can be seen. In the lower left corner, you find the likelihoods of our resulting sampling without prior information. where yellow represents high likelihood values and blue low ones. The solution algorithm searches a wide area with multiple maxima. In the upper right corner, the study is performed with prior information. Compared to the other study, the distributions detected are more narrow, with only single maxima. This leads to more likely results. The prior information pulls the solution towards it, not scanning a bigger space and therefore risking to stay in a local maximum. Nonetheless, both studies show acceptable results. In order to investigate the limits of the inverse characterization, we performed two parameter studies. First, we raised the number of load cases which are used to calculate the results. Therefore, more measured strain data are available and the result is more likely to improve. 10 repetitions have been performed and the root mean square error of the inversely characterized ply angles to the true angles is calculated. The diagram shows a reduction of the error till 3 to 4 loads and then converges. The second study increased the number of layers to be characterized. Therefore, more unknown parameters are included into the solution. The root mean square error shows the increase till 7 layers and then stagnates. The error values are lying between 5 to 10 degrees, which is rather high and not acceptable. To conclude, I gave a brief motivation on why the digital twin can benefit from inverse characterization. I presented a method to estimate composite laminate parameters and applied it to a use case showing the effect of prior information. Further research activities have to face experimental validation and the extension to more advanced models like FEA models. Thank you for your interest in the topic.
Thank you. And the final presentation is on diverse system level design using manifold learning and partial simulated annealing by Sushmit Shah, who is a principal scientist at SRI International, leading the research group of neurosymbiotic computing and intelligence. His research focuses on combining formal methods and machine learning to build trusted artificial intelligence and correct by construction cyber-physical systems.
Hello, everyone. I'm Sushmit Shah, and I'm going to present a paper on diverse system-level design using manifold learning and partial simulated annealing. This is a joint work with Adam Cobb, Anirban Roy, and Daniel Elenius in Computer Science Lab at SRI. This work is a fragment of the Trinity AI Co-Designer, a system that we are developing at SRI as part of DARPA's program on symbiotic design of cyber-physical systems. We realize that design, unlike many other learning problems, is a challenge of learning from small number of examples. And hence, we need to be able to combine inductive learning with the deductive reasoning to understand the cause of failure and success of different example designs. Our goal is to create a digital twin that can be evaluated and simulated using existing scientific tools. Further, we aim at being able to address a major challenge in design of cyber-physical systems, which is the absence of complete specifications. And we do so by being able to generate a diverse set of designs that satisfy any given partial specification. These are examples of designs from the Trinity system currently that we can generate for unmanned air vehicles, and you will see that there is a whole different diverse set of designs using propellers in different topology and combining propellers with wings in a novel way. A key component of Trinity is the ability to be able to do parameter exploration and be able to optimize multiple objectives using a set of surrogate models. The key idea here is that we sample a bunch of example designs, and we use that to be able to learn a design manifold using a variational autoencoder. So X denotes here all the train points that we have, the example designs, and these designs don't need to be designs which perform great. They just need to be example designs. And once we have learned the design manifold, we also concurrently actually learn the mapping from the latent space to a specification network that tries to predict different design objectives. And another critical component of this piece is that we need to be able to make the entire setup here uncertainty aware. So what we do is that we use dropout in our decoder network to be able to quantify uncertainty in our prediction. So that if we take a particular new point X, we are not only able to predict what its specification, the objective values would be, but we are also able to assign how confident we are about these predictions. And then once we have learned this, then the design exploration and optimization is done using a Hamiltonian MC-MC walk over this design manifold, where we optimize these different performance objectives, keeping into mind the uncertainty, the probability of how good our prediction is going to be. And we're going to demonstrate this approach over the design of propellers, which is a subsystem that is common to unmanned air vehicles, urban air mobility vehicles, as well as unmanned underwater vehicles. We use OpenProp, which is a simulation tool used even for manual design of propellers, as we are using OpenProp as our scientific model, and we use that to generate data from which we learn the surrogate model that is then used to do the design. The specification here is a range of velocity at which we are expecting the propeller to operate, and we require the efficiency within this range to be high. We also have some thrust requirement, that is, the propeller should be able to generate some minimal amount of thrust. And the design space comprises a number of blades. We need to choose at what RPM the propeller is going to operate, the diameter of the operator, the diameter of the hub, and so on. So these are the parameters and the ranges the specific ranges we're using in the design problem. And what we have observed is that our approach is able to speed up by a factor of 100x exploration using OpenProp directly by essentially building a hierarchy of these surrogate models and exploring over that rather than directly interacting with OpenProp. And the relative error that we observe is less than 2%. These are all the design parameters that we are exploring the propeller. And here what we will observe is that all these orange points are the prior sampling, which is obtained using the trained data, which are these green samples. And the blue regions are essentially the samples generated from our approach after optimization. And you will observe that our approach is able to achieve higher efficiency even at lower velocity, which is a difficult multiple objective optimization criteria to be met. And one thing critical for our approach is the ability to be able to understand when we cannot trust our surrogate model. So here you're looking at, on the x-axis, the sample for our HMC walk. That is how we are optimizing. These are the optimization iterations, essentially, each iteration being one sample. And what we observe is that as we start observing higher velocity and higher efficiency, we also notice that the uncertainty has gone up, at which point we will terminate and we will know that we cannot trust a surrogate model beyond this. So we should be reporting this as our result. And looking at the same data, but in a slightly different perspective, here what we are looking at is efficiency versus velocity. The uncertainty that our model predicted, these red points are the high uncertainty points, and this is the actual true error. And what you can observe is that our model is able to very correctly predict when it cannot be trusted, when the error is going to be high, which helps the optimization to be able to ensure that we only optimize within the trust region of the surrogate model. These are different designs that we create, and you will notice that they are quite diverse. We have different number of blades, different diameters, and so on. And on the right-hand side, what you're seeing are the designs created through direct optimization using evolutionary algorithms, and we observe that they are quite similar in nature. So our approach is able to maintain higher diversity. Thank you.
Okay, thank you to all of our speakers. And now I open the floor for questions. We have quite a few in the chat. Feel free to add more. as we continue our discussions. So the first question, which I would like to ask Molla, is actually by our other speaker, Sebastian. So Sebastian can also elaborate further, but Molla, Sebastian asks you, if your data set consists of human design process steps, did you thought about using artificial weights to increase your data set?
Yeah, it's an interesting question. So actually, we were thinking to generate some artificial data from the existing data. But the thing is that we are considering also the design cost and their outcomes. So when we generate some artificial data, say the sequence of data, that not actually provide us that the performance. So in that sense, particularly for this problem, we actually do not generate data. But in some cases, like if we want to get some actions prediction based on the historical data, in that case, I think that data generation is a very good idea. Yeah.
Okay, Sebastian, would you like to add anything else, or that answers your question?
No, I would just like to thank Molla for this, for answering the question. Yeah, that's exactly what I asked.
Yeah.
Okay. I'm very sorry, I keep calling you Michael. So, Michael.
Michael is totally fine.
Thank you very much. My apologies. Michael, ask you. You state that the high-performing designers follow certain strategies and patterns. Can those be formalized to, for example, a procedural approach for design automation?
Yeah, that's a very good question. And actually, that's our motivation. Like, if we can get some strategies or get some patterns that particularly from the good high-performance designers, that can actually be used for any existing algorithm for that particular pattern, that could lead us some design automation or even for artificial agent. So that's the main motivation. Yes, I think we didn't look into that, like how we can use those pattern into the any existing model. But I think that is a very good direction. Like if we use that patterns or the strategies that can actually be formalized. Yes.
I would like to follow up on. Oh, sorry.
No, just go.
Please.
Maybe a short follow-up. What steps would be needed to do this formalization?
Yeah, that's the things, like, because we didn't look at that system that the things yet, but I think maybe some I'm not sure, like, but maybe some existing methods that actually use this kind of formulation or this kind of pattern or design automation. In that model, we can use that kind of this kind of strategies or design patterns. Or even like if we provide this kind of strategies manually for any designer, say like if you can follow this kind of strategies when you design, I think that is also actually can help the designer to to within short time they can reach the goal, or their design can be more efficient.
I would like to follow up on that. So just to be clear, what I got from reading your paper, and I don't know it was also stated in the presentation, but it was quite a short presentation, so you could maybe elaborate on that a bit more. Yeah. What I got is that you actually have a twofold objective of your approach, because you're in a one way trying to mimic human behavior, which is not optimal. We all have our biases and peculiarities, and the other. So you're trying to mimic that and in order to predict what the human is going to do next. But on the other hand, you also want to be able to optimize to push them in the right direction, right? To actually know what the optimal way to design something is, right? And that's actually okay.
Yeah.
Sorry.
Yeah, here the optimality is we are not looking at that optimality, but we are looking for from the designer's perspective optimality. From our data sets, we identify who is the high performance designers and who is the low performance designers, and based on the high performance designers, we assume that their design actually is optimum, and if we follow their design, their design could lead us to good design. So in that sense, we mimic their design, like how their design would lead us to the good design, and we identify some of the patterns from that design.
But did you? I don't know. Didn't see it in the slides. Did you also take a look into what the other patterns of actually low performing?
Yeah. We actually in the paper we actually discussed. We actually seen like some of the designers in the low performing designers, they use some of the redundant patterns like analysis to analysis. I mean, like when we analyze something and in the next time you do not analyze the same thing again. So it is a very redundant pattern. So this kind of pattern actually do the low performing designers, which is actually very time consuming for design. So we actually identify that kind of design pattern also. Yes.
Okay, so you actually analyze both high performing and low performing designers, right?
Yeah.
That's great. And so did you just another question, which I assume is covered by machine learning part of this, but given the expertise of a designer, maybe one suggestion would confuse someone, given that you have a system that is actually going to help me make suggestions what I should be doing next.
Yeah.
And if you suggest like now you should be doing analysis after this stuff, it might actually confuse me if I'm a novice, and it actually might be helpful if I'm an expert. Do you account for those kind of differences?
Yeah, I think that's the good things. So for that things, we didn't actually use the, so, like in our case, we use some of the action. I mean, like we categorize the action of each of the actions, say like analysis or even the add. So when they add something, so we didn't actually we didn't tell the designers like you add this. So we just tell that you add, and you can add anything like in that. So it is your preference, like which thing you can add, like add wall or add roof based on his design procedure, like it stays in that design. So that's the preference they can have. But that's a good question. Like if some designers may be, they can be confused if they have we didn't consider that yet, but that's a good question. Yes.
Thank you very much. If we have enough time, we will come back to your interesting work, but I would like to now move to questions for Sebastian. So we have, I accidentally muted myself. Okay, so we have a question for Sebastian. And Michael, again, states that do the detector spheres lead to ambiguous pictures as input for your CNN, or is it possible that several geometries lead to the same image?
Yeah, thanks, Michael, for the question. In general, it does generate different images. That's the whole idea of it, to have a standard component and then transform it to different images. But of course, in the same class, there should be a similarity of these generated matrices. And the results show that there is a difference. Otherwise, it wouldn't be the CNN wouldn't be able to classify these input matrices. But of course, depending on the way you are generating these or you are conducting the projection, there are ways that things are not well transformed. So you have always some kind of error. And in this case, what should be a problem is if you have hollow parts. So if there's, for example, if you have a ring and then a ring that is hollow but has no through hole. A through hole is no problem, but if it's just hollow on the inside, this would be a problem to differ between these two matrices. But in general, for this data set, which consists of basically a lot of technical and norm parts, it seems to work.
I would like to follow up on that. So have you maybe, when you said that you have the really high accuracy on your classification task, but have you looked at misclassified examples where they're like rings and stuff like that? Okay, so that's, or not?
This was just a general part. The ring is not a part class in this data set.
I know.
But with the confusion matrix, it's possible to see which classes perform very good For example, screws in general will perform very good, but some classes have or are more difficult to classify. For example, gears are because they are very large, and then with the detector sphere around, there is the problem that there is there is a larger error, and these are just two examples of parts that work and parts that don't work at the moment as good as the others. So I haven't in the paper I haven't really listed the different classes and their specific classification accuracy, but yeah, it wouldn't be a problem to see which parts work and which doesn't.
I asked because they point towards what might be, you know, the shortcomings of your approach. But you also stated that there is one benchmark performing better than your model. Otherwise, your approach was really good. Is there? Can you please comment on that? Why do you think this difference is, and what can maybe, you know, improve to get ahead?
Yeah. Of course, the net that was better was the rotation net, and it uses a multi-view approach. So it, in general, it uses a lot of viewpoints around the part, and then for every image that is rendered, a different CNN is trained, and then it's again pooled to another CNN, and then the class is classified. So of course, there's would be an idea to add this kind of general idea of using multiple views around the part, and then see if this gets to a higher accuracy. And but my idea was to transform as much information from one part into one image or matrix. And so another idea is, of course, always to train on the hyperparameters for transfer learning to achieve a better accuracy, or that's another idea to improve the input, and therefore to get an alignment that is specific for CAD parts or cut parts, because in general there's an idea behind how you generate cut parts, and to get this in the alignment idea, and therefore maybe improve the results. So this there are the two main things. One, the alignment, and the other one is also to do a multi-view approach, and maybe this would improve then the results compared to the rotation net.
Great, thank you very much. Are there any other questions to Sebastian?
Maybe a short question, thinking more to the future, what you could do with your approach, because I really like what you're doing with it. Do you think it is possible to inversely use the approach? So what you did is sort of classification, so you can find different screw types or some bearings or something like that in assemblies. Do you think it is possible to do it the other way around? So you say you want to get or design a screw or a bearing, and your neural network can make some suggestion for geometry. So you get into the direction of automated design.
Okay, that's I haven't thought about this idea, to be honest, because I just thought about using this information of the class label to improve other steps, for example, FEM preprocessing or assembly retrieval. What you suggest is then I'm not quite sure right now, because you must transform the geometry in a way and compare it with another transformed geometry, and then retrieve the other geometry from the matrix. So yeah, like you said, it's the inverse way, but I always thought of it more than a one way. So because in this transformation step you lose some kind of information, so it's not 100% reversible. Therefore, I'm thinking it would be quite a challenge.
Okay, thanks.
But yeah,
I have a question. So So for your model or any other model that for comparison, so do you think which model will be good for generating new design or optimized design, like using the GAN or any model? So do you believe that your model will be perform good if I use the GAN or any generating model?
Sorry, I didn't understand the question.
So I mean, like, so because I mean, like, if I want to generate some new design from the existing part of the mechanical part of, like, it is like optimal design or anything, using the, like, generating new design, like the GAN, how the GAN work. So so if I use your model from using the to create a GAN model, will that work well, or any other model like the PointNet or any PointNet++? They have the similar kind of model. So which model do you believe it works better for the GAN model or any other generating model?
Do you mean for GANs for generating new designs?
Yeah.
Okay. Yeah. That's also I haven't looked into GANs and how they compare with PointNet. So I think they maybe they are using the feature vector, and so this would also be possible, but to be honest, I'm not quite sure how GANs and PointNet are connected. So I would have to look into this, and then I could say, but PointNet in general also transforms the points to a CNN. So there should be a connection, because then the pre-processing step is different, but then the computing and machine model learning step. There should be a similarity where things could be connected.
Thank you. Yeah.
Thank you. We are now going to move to Binyang. Binyang has been talking about machine learnability of image and graph representations, and we have a question from Bickel. Did you investigate how your approach performs compared to optimization using physics-based models?
Yeah, I'd like to answer this question from three aspects. Sorry.
Okay. Sorry. Continue, please.
Yeah, thank you for the question. Yeah, first, compared to physics-based simulation, I think the deep learning model, the average prediction error for different performance metrics is about 4 to 9%. The average prediction error. So yeah, it for the current model, there is still room to improve the prediction accuracy. I think the one issue here is the current training set is small. We only have around 1,700 samples in the training set, and this training set doesn't cover the design space very well. That means there are some very sparse spaces that the training data doesn't cover it well. So I think after we have a larger training set and cover the design space better, the prediction accuracy can be improved significantly. Yeah. Then compared to the simulation models, the time efficiency for the deep learning model is high. Yeah, it's much higher. Then another advantage of the deep learning model is, for example, we have discussed around the generative models here in this session. If we would like to evaluate the newly generated designs from the generative models, if we use the simulation-based method to do this, we need to export the new designs from the model, simulate them, and then send the simulation results back to the model. But with the deep learning model, we can connect these two models. So we don't need to export the new designs do the simulation and send back the results manually. We can seamlessly connect these the generative model and the simulation model to speed up the training process of the generative models. Yeah, that's my answers to this question.
Would you like to follow up, or you're satisfied with the question? Okay, with the answer.
I'm fine, thanks.
And we have another question, which is it possible to add an attribute to the graph node, like a rotor or battery, etc., and therefore expand or improve the vector of for each node?
Yeah, thank Sebastian for the question. Yes, the short answer is yes. We can add the attribute to the node embedding. But for the current graph representation, actually we have already included this attribute in the node embedding. Yeah, we use one-hot encoding to include. In the presentation, I name it as like component type. We have 4 values or element in the node embedding. Each corresponds to one component type, like rotor motor pair, battery, or airfoil. If they, for example, if this component is a rotor motor pair, then the value for that element will be 1, and the values for the other component will be 0. So we use one-hot encoding to do this. Yes, I think the drone design space we used is a simplified design space, like we think the components from the same type from, let's say, if the motor rotor pair, they all have the same design, or let's say same geometries, something like that. If we have more detailed design parameters, we can expand the node embedding to include the new design details of drones. Yeah, it's possible to extend the node embeddings. And I think, yeah, that will also allow the graph to convey more design details of the drones.
You also had an open question at the end of your presentation. Would you like to reflect on that open question?
Yeah. For example, now we have some studies to previously when we do simulation, especially for FEA, we have some mesh representation of geometries. I have seen some studies, they convert the mesh of geometries to graph representations, like each node of the graph is a node in the mesh, and the links represent the spatial relations of the nodes in the mesh. And I have seen some studies have reported the graph representations actually can improve the save time for running complex FEM simulations. And say, yeah, actually we can capture the physical relations of elements in a system. But a question for me is, for example, let's say in the drone design, actually we can capture the spatial relations between different components. But in practice, when a drone is when a drone is flying, actually there should be some like force or force interaction or torque or mechanical interactions between the components. For this part, the current graph hasn't captured these features, like how the force from this rotor influence the force from a different rotor. We haven't captured this kind of relations. So I think it's possible in the future. It's possible to add more to make the graphs capture more relations between the components.
Well, thank you to that for that. If any of you have any questions or suggestions related to that question, feel free to edit or either now or after the session and comment with Binyang on her open question. It was basically directed to all of us, so we should be moving next. So I have a question here that states for Bickel. I'm very sorry. I don't know why I cannot learn your name. It's incredibly easy. It's just not going out. So how can the prior information for achieving better results be obtained?
It depends a little bit on the application. So what we did was, or what we wanted to do was inversely measure the variations of the ply angles, which can result from manufacturing. And in this use case, we want to measure variations to nominal design parts. So we have the nominal design values and can use them for our prior information and for the prior distribution. So getting the wideness of the distribution. Yeah, you should typically use information you have from former products. So if you're designing something and you have further older generation of the part, maybe you already know some variations that occur in the part. Or if you don't have this information and this data, you still could be using data from literature or from general knowledge, how good and how precise manufacturing technique will be. But overall, it's always a bit of a problem to get to this data. It's always quite an effort to measure the data and prepare the data for such tasks. So as we saw in the studies, it's still a bit better or still good enough to maybe choose some wider distributions for the prior information. So not being so confident in your prior information, this will lead to literally the same or pretty the same results, but you just don't need to be so precise with your prior information.
I just wanted to, that was what actually I wanted to ask, because you said, and it's quite evident from your results, that prior information improves the performance, but it also might lead you to local minima and where you get stuck, right?
Yeah, this was the first study I performed. So prior information is good in the sense that you're pretty fast at your maximum, but if you're not really confident in your prior information, it's you should more likely choose it a bit wider or just leave it out, because you get more detection of the design space. So you're more likely to find other maximum as well, and therefore be more likely to find the best solution or the best true values. Yeah.
Thank you for that. If we have time, I have another question for you, but I'll move to Sushmit, who has actually 4 questions, if I counted right in the chat. So let's move to the first one, which is by Molla, who asked, when you generate different propellers, do you consider the cost as a constraint? And if not, will the model work if we set cost as a constraint?
So thank you, Molla, for the question. So our approach takes multiple objectives. So we can have different performance objectives, different cost constraints, and we try to learn a surrogate model and then do a multi-objective optimization over that. So yes, we can take cost as a constraint, but the challenge is that how do you get a good model for the monetary cost? For the air vehicle, it's easier to do that because we have cost associated to motors, propellers, and we have observed that costly motors tend to create better designs. But for propeller, getting a cost estimate is not easy in a more sort of digital framework where we are trying to rely on simulation models. So we do not take the monetary cost into account, but we can deal with as many objectives as are given to us.
Another question is by Binyang, who asks, how are the generated designs evaluated, through simulation or through surrogate models?
Right. So Binyang, we evaluate, the final evaluation is done against the simulation model. And to be very specific here, we are using a Creo, which is a sort of a model which can allow you to do FEA, to be able to do drag and lift computation. And then we feed that into a flight dynamics model. The flight dynamics model is proprietary, has been something that has been developed over 20-25 years for the aircraft design. For the propeller one, it's OpenProp, which is publicly available. So that's the final simulation model, the evaluation model that we're using. But during exploration, we rely on the learned model. And the key challenge is that how do we make sure that when we sample a configuration and we use the learned model, can we actually trust the output of the learned model? Or should we go and evaluate it on the detailed simulation model?
Got it. Thank you for the answer. Yeah.
And maybe I can answer the follow-up right away as well. So how does the model increase the variety? So the idea here is that we are using Hamiltonian MCMC, which is sort of an MCMC which comes with a potential function attached to it. Mm-hmm. And what we can do is that we can look at multiple different objectives and treat the potential in a way that allows us to be able to not just optimize, but go in different parts of the design space. So essentially, you have the potential energy and kinetic energy, you can trade that off and be able to trade off diversity versus optimization.
Okay, so actually the decoder is trained to consider the multiple objectives at the same time.
Not the decoder, but the specification network that is attached to the latent space. That's the one which is written the objectives. The decoder is only meant to make sure that we are learning the latent space correctly. And also
so the latent space is manipulated to increase the variety of the designs. Okay, got it. Thank you.
And it's a small world, Binyang, if I can just quickly mention, I think your collaborator, Chris, works closely with us, so we can have a longer chat later on.
Sure, thank you. Yeah, we can chat there.
So you have another question which is related to diversity, and the question is, why is high diversity good? Why we actually want it?
Yeah, thank you, Michael. So this is a very interesting question and sort of the origin of why we try to do this. So what happens is that typically you don't get full specifications ever. Many of these systems are developed over years and decades, and specifications change. So imagine you're trying to develop an aircraft whose main purpose was reconnaissance, and you designed an aircraft which is perfect, except that when it flies, when it turns, it makes a high degree roll. And suddenly a new specification comes in that maybe we want to use this aircraft also to do firefighting. Now, this is a big mismatch. You have to restart your design from scratch. If you had maintained a diversity so that those parts of the design which are not fully specified, you had multiple different choices made there, it is more likely that when specifications change, you'd be able to adapt to it. So that's the sort of primary reason why we require diversity. A secondary reason is also that the simulation models themselves are not perfect. So imagine, for example, very complex physics, which would be, in our case, the interaction between the propeller and the wing. Now, how the airflow has to be modeled between propeller and wing is difficult. Many of these simulators are not perfect at it. So you might end up creating a design which looks great against a digital simulator, but when you fly it around, you will fail. So if you have diversity and you have made choices which are hopefully exercising at least some parts of which are not exercising any part of the simulator, which is faulty, those designs will work in practice. So diversity for two reasons: A, specification being incomplete; B, the simulation models themselves not being perfect.
Thanks a lot. Maybe a short follow-up. Are these diverse solutions, are they of equal quality? So is there some kind of fitness function or something like that, which is very similar in each solution?
So because we are working in a multi-objective space, and we didn't want to reduce it to a sort of a scalar space by defining an arbitrary fitness function. When we say diversity, we mean diversity in terms of the design choices we are making, also diversity in terms of where we are in the Pareto optimal sort of objective space. So we try to avoid designs which are dominated. That is, the design will be worse than at least one design which is already discovered. But the way Hamiltonian MCMC works, we cannot guarantee that. So at the end, you get designs which are promising and are diverse in both the objective and the configuration space.
Well, with that, I would like to, we are running a bit behind the schedule. So I would like to thank all of you for the wonderful presentations and the discussion. I really enjoyed it. So if you have any further questions, would like to catch up, it's a perfect opportunity to join Gather. We have a link in the chat and also in the middle of your screen. So grab a beer or whatever and join us in the Gather. Otherwise, I would like to say thank you to all of you. Congratulations once again to, of course, all of you, but especially Sebastian and Sushmit for exceptional performance. You will receive the certificate, the reviewer's favorite certificate in the email and in the mail, postal mail. After the conference, unfortunately, we cannot handle it to you live. But thank you all, and see you in Gather.
Thank you, Majda.
Bye. Thanks for sharing.
Thanks for sharing. Goodbye.
Thank you.